Okay, so here we are continuing with activity 2.1.7, number 4. This is called the method of joints that we're going to do, and now we're going to determine the internal forces on these members in this truss. So, and the members that we need to find are member AB, member AC, and member BC. And because these are some type of bar or post of some sort, they're going to either be under tension or compression and going to have some force there on that as well. So we got to use what's called the method of joints to come up with that. Now I've already redrawn these here with our forces going the direction that we have. And the best way to do this is we're going to split these apart. So I'm going to basically cut each of these members in half. And we're going to make arrows going away from each joint here. And then we're going to have to draw some free body diagrams of both of these. So we'll end up with free body diagrams here. Well, let's go ahead, we'll draw the free body diagram at joint A first. So, well, and we got here, we got a force here, we got a force here. Now, this is the force of member AB. This is the force of member AC. And we also have a force of 50 pounds, which we determined 50 pounds because that was actually the force of AX on our roller up here that we had determined earlier. So we can go ahead and just use 50 pounds right now because we already determined the force of the roller, or that reaction force, to be 50 pounds here acting on that. So that's joint A. We do our free body diagram here at joint B. So we've got the force of BY, which we know that to be 50 pounds from earlier. We've got the force of BX, which is 50 pounds. We determined that earlier. We've got the force coming at an angle here. This is the force of BC, and then we've got the force coming down here, and we're going to assume that it's going down there, and this is the force of AB, or BA. You can call it either way, but I'm keeping my terminology standard here. We called it force of AB over here. We could say this is the force of BA, but it's really the same thing. What we're doing is we're trying to find the internal force of that member, whether you call it force of AB or force of BA. So that is our free body diagram for joint B. Now we want to draw the free body diagram for joint C. And here we've got our 50-pound force here going down. We've got a force here, which is the force of AC. Again, we're keeping our variables consistent, but we could also, if we're going from this way, you could label that force of CA, force of AC. Either way, we're looking now for the internal stress on this member. And of course, we got the force of BC going up this way, force of BC. Now we've got a decision to come to. We've got to kind of decide which one we want to solve first. And how we decide that, well, we're going to go with what's the easiest one to solve, which in my mind is this here, because we all have either horizontal lines or vertical lines and forces. We don't have to deal with the angles that are on the other two. And here we got 3 forces here, we got 3 forces on this one, we've got 4 forces on this one. So we definitely don't want to do this one. We want to save that one for last. Because of this angle, that's going to make this one a little bit more complex. So I'm going to stick with this one first. And here, when we're doing method of joints, all we have to do as far as our statics equations is the sum of forces in the x equals 0 and the sum of the forces in the y equals 0. We don't have to worry about moments on that at all. So, and again, looking here, so we made the assumption that we're going away. So let's go ahead and let's set this up for joint A, and I'm going to try to keep this as neat as possible. So joint A, sum of the forces in the x equals 0. So my forces here are 50 pounds plus the force of AC. Okay? Solving for 0, we find out that the force of AC equals minus 50 pounds. So what does that minus tell you? So, well, that tells us that we were actually wrong here. So our direction on this force is actually going the opposite direction. So we need to move this back going this way. So let's change this. So as we originally thought that force was pushing it and going out that way, we're realizing that it's going this way. So we are actually here with force of AC is 50 pounds, and that is in tension. So force of AC is in tension. And we came up with that. Now let's go ahead and sum of AB. So the sum of the forces in the Y equals, all we have here is force of AB, which equals 0. So sum of the forces in Y equals 0. So force of AB is the only one there, so force of AB has to equal 0. So here, the internal forces on this are 0. So we're in neither tension or compression on that whatsoever. So that is joint A. Now we need to go ahead and decide to make for the next one. So let's do some replacing here. We know now AC is got 50 pounds on it. So we know what this is. 50 pounds. So, and we know that force of AB here is 0. There's nothing on AB at all. AB equals 0. AC equals 50 pounds. So when we come over here now to solve AC, we're in good shape here because we have this force of AC. We can go ahead and replace this with 50 pounds. So, alright, now to get force of BC, we're going to have to come up with the components of force of BC, the X and Y components. So let's, real quick, we're going to do the trig here on this. So we have our, I'm going to do this a little bit bigger for you, just so you see this. So we've got force of AC, which is 50 pounds. We got this 50 pound force down here. And we got the force here of BC. Now, we've got our force of BC in the Y, and we've got our force of BC in the X as well. So, now, we're going to have to use some trig here to do this. And if we know from our drawing up here, we're 3 feet by 3 feet. So that lets us know we need to calculate the angle. So, but that's 45 degrees. So, and the way I know that is we've got our different equations. So it's sine of theta equals the opposite over the hypotenuse. Cosine of theta equals the adjacent over the hypotenuse. And tangent of theta equals opposite over the adjacent. So if I look up here, what two sides do I have? So if I'm looking at this as my angle, 45 degrees here, well, my opposite is 3 feet, I don't know my hypotenuse. The hypotenuse is the longer side. So what I've got here is I've got the opposite and the adjacent. So I come back down here and I look, well, the formula that I can use here is the tangent of theta equals the opposite over the adjacent. So tangent of theta equals 3 feet over 3 feet, which is 1. So then I need to find theta. Well, theta is the inverse tan equals the inverse tangent of 1. And if you plug that into your calculator, you'll find that theta equals 45 degrees. So that's how we determine that. Make sure when you're using your calculator that your calculator is in degree mode and not in modian, or not in radians. So I'm going to use f of BCY and f of BCX to help me determine out what my real value here is of force B. But let's go ahead and start this out. So sum of the forces in the X. What do we have? We've got negative 50 pounds, and then we've got plus force of BC in the X. All right. So now again, notice if we're going this direction, so we're assuming that is going negative as well. We're not sure yet, so we'll have to come back to that. So force of BCX equals 50 pounds. But it is not force of BCX we want to find. We need to find the value of BC. So how do we do that? Well, this is where we need to use the trigonometry. And again, here we've got the opposite over the hypotenuse, and that is our sine. So we got to break this up. BCX, the force of BCX, we got to find that in a trig relationship. So if we sit here and we look at it using the sine of 45 degrees equals f of BCX over f of BC. F of BCX equals f of BC sine of 45 degrees. So now here we're going to plug in and substitute. So this goes here and replace this. So 50 pounds equals f of BC sine of 45 degrees. Now the sine of 45 degrees is actually 0.707, so we can go f of BC equals 50 pounds over 0.707. If we divide that out, f of BC using our calculator, so come right in here with the calculator. 50 divided by 0.707 equals 70.72 pounds. We'll leave that there. So now we found f of BC. F of BC here is 70.7 pounds. All right. And now we found all three of these, and we know whether they are in compression or tension based on the numbers that we have discovered. So we could do the same thing. In this case, I only need to find one or use either joint B or joint C to give me all three of the internal forces. So I don't really need to do anything with joint B. However, probably not a bad idea to use joint B to double check your work. So we can double check our work here and just see. So let's go in here with joint B. So when we've got the sum of forces in the X here at joint B, we've got equals 0, that equals the force of BX, which is negative 50 pounds, going that way, so 50 pounds, and up here, let's go ahead, let's break this down into our components. So we've got the force of BC in the X, and we've got the force of BC in the Y, force of BC in the Y. So negative 50 plus the force of BC in the X. And we'll go ahead and do our y here as well. So the sum of the forces and the y equal 0. We got the force of AB, which we already determined was 0 pounds. So, plus the force of BY, which is 50 pounds. Let me write this out too. So just say force of AB, which we know is 0, plus the force of BY, which we know is 50 pounds. And now we also have to go minus the force of BCY, that component force, which again we don't know yet, minus force of BCY. Alright, we end up with minus 50 pounds equals minus the force of BCY, or the force of BCY equals 50 pounds. Okay, again, this is incorrect. So, because we're not looking for the force of BCY, we're looking for the force of BC. So again, we've got to replace this BCY with some form of the component of BC. And again, we're using trig here to do that. So, again, as we look at this, so we've got the cosine of theta equals, here's our theta angle, equals the opposite over the adjacent. Now in this case, the sine of theta would be, so sine of theta equals the opposite, force of BC and the y over the hypotenuse, which is the force of BC. So, and we can also use the cosine of theta equals the adjacent, which is the f of BC and the x over f of BC. Same thing. So f BCx here, we ended up with cosine in this case. So f BCy is sine, and we're just going to replace that into there, and we'll end up with the same thing, so that we determine that this indeed, we've got 0 internal stress here, we've got 50 pounds of compression force here, and we got 70.7 pounds of tension here in this member. So, hope that solves and helps us to calculate these out and get the correct answers as we're going through these.